So in this video and the next one, we're going to look at solving exponential equations. So to recognize that you have an exponential equation, the idea is that when you look at the equation, you have your variable is stuck in an exponent. So we've looked at these before, but what we did was solving with graphing. So what we want to do now is solve algebraically, now that we have logarithms to help us out. So the two forms that we're going to look at in this video in part one, we're going to look at these cases where there's only one exponent with your variable kind of stuck in there. In the next video, what you'll see is we'll have a different process for when you have your variable stuck in two separate exponents and what we'll need to do for that. Now, I will say the method we go through in the second video would work in this first video as well. It just tends to take a bit longer. We can revisit these once we talk through the second video and see how you could use it here as well. But these steps tend to be a bit shorter and also line up a bit better with how we've been talking about logarithms so far. So our first step is that we're going to isolate the exponential term. So that means a term where we have some base and the exponent that has our variable in there equals a value. So if anything else is multiplying, dividing, adding on outside of the exponential piece, we're going to want to move that over to the other side of the equation first so that we just have base and exponent equals a value. Because then when we have that form, we can change to logarithmic form, meaning we can now switch it to the exponent equals the logarithm of some base of the value. So in our first example here, and I'll come back to these steps, but let's do this first step where I have base exponent equals a value. So I don't need to do anything for step one there because it's already all isolated. But now what I'm going to do is change to a logarithmic form. So we're solving for our exponent. So we'll have x equals a logarithm with base 3 of 15. Now, in terms of an exact answer, that's all done. What we could do, it's not too bad to do in this case, is checking our answer. If we wanted to check with this exact form, so 3 raised to the log base 3 of 15, and we want to know, does that equal 15? Well, that uses that process where the base of the exponent matches up with the base of the logarithm. So it's like those two pieces cancel each other out. So we would have 15 equals 15. Now, something we're going to want to do here, though, is look at the, how do I want to say it, the rounded answer, the decimal form of the answer. We'll want to see that, especially as we get into word problems. So this is where our change of base formula comes in. So step 3, solve the equation using methods. We didn't really have to do any solving here because it was just x for our exponent. We'll see that come in this third example where we'll have to do some stuff with x once it gets out of the exponent. So then to get the decimal estimate, the estimated form, that's the word I was looking for, is we'll want to use the change of base formula. So where you have logarithm base n of some value m, you take the logarithm of m in the numerator divided by logarithm of n in the denominator. And again, you can also, so you can use log base 10, or you could use natural log. Out of habit, I just usually go for natural log. I think that comes from my old calculator had a natural log button, but not a log base 10 button. But with our online calculator, we have both because we're just typing it in. So either way is good. So with that, let's get a decimal estimate here. So we're going to say x equals, and what we're going to type into the calculator, let's do natural log of the value of 15 over natural log of 3. So the bases of the logarithm have to be the same. Value goes to the numerator and base stays in the basement and goes to the denominator. So let's go to a calculator. So here I'm going to make a fraction. I'm just typing in ln on the keyboard and then parentheses 15 over natural log of 3. which is, I'm going to go to 4 decimal places here. So to right there, which would round up the 9, which would make that a 0 there. So we're going to have a 2.465. So with this form, we could also check our answer just to make sure we did this all correctly. And what we would do is do 3 to the 2.465 and see, does that equal 15? So we'll go to our calculator there. We go 3 raised to the 2.465. And as you can see there, it isn't perfectly 15, but that's because we rounded up above here. So by rounding a bit there, we're introducing some error. So that's really close to 15. Like, the idea should be that if you round it to a whole number, it should land at the correct value, and that worked out great. So that checks. So we're all good there. So for an estimated solution, we have the 2.465. For an exact solution, we have the logarithm base 3 of 15. It just depends on what they ask for. In this video, I'll show you both solutions for each of these. Okay, with this next one here, I can see the base and exponent, but I have this 3 multiplying on the outside, so I need to move that away. So I'm going to divide both sides by 3 first, so that we end up with 2 to the power of x equals 15 divided by 3, which is 5. Now in this form, we can change to logarithmic form. So we're going to have our exponent of x on one side of the equation, logarithm base 2 of 5. So that would be our exact solution. If I wanted to estimate, I'm going to use the change of base formula. So log of 5 over log of 2, and get a decimal estimate of, if I go to our calculator, I'm just going to go ahead and edit up here since I have the form all set up. So that'll be a 2.3219. And then we want to check our answer. So we're looking at 3 times 2 to the 2.3219, and we want to see if that equals 15. So going to check our calculator. Let's see, exponent of 2.3219. And again, it's a little off because of the rounding, but if we rounded that to a whole number, it would be 15. So we're all good there. So with that, we have our estimated solution and exact solution. All right, our last one here. So we have base, exponent, and value. Now our exponent just kind of looks larger than these other ones, but really it is all this value in the exponent. So changing to logarithmic form, that entire exponent will be alone on one side of the equation. So we'll have x squared equals logarithm base 10. So I don't need to write the 10 there, of that value of 8. So then what we would do, and this is where step 3, I use that wording of solve using methods we've used before. That might come through as a linear equation, that might come through as a quadratic equation, like in this case, where we need to take the square root of both sides. So I'm going to take square root. So that would give us x on the left-hand side. And then if we take the square root of both sides, we would have plus or minus, which is very important to include because we're ending up with 2 possible solutions here. And then we'll have this square root log of 8. So getting a decimal solution, getting an estimate, we're going to have 2 possibilities, the positive and negative version of this number. So what I need to do is take the square root, log of 8, and that's a 0.9503. So we'll have the positive version of that number and negative version of that number. So we need to check our answer. So we're taking 10 to the 0.9503 squared and seeing if that equals 8. And then we're doing the same thing, but with negative 0.9503 squared, which, as long as we're using our parentheses correctly, that's going to just turn out to the same number, because when you square it, it'll make it positive. So with that, let's just go to our calculator and have 10 with an exponent of 0.9503. And then we're going to go ahead and square that. As you can see, that would round to a whole number of 8, which is perfect. And same exact thing if there's negative in there. So that all checks out. So we have our estimated solutions and our exact solution. So again, this is a case where our variable is only showing up in a single exponent, but we should be able to isolate it and then switch to logarithmic form. But in this next video, we'll see how we get stuck with this just changing to logarithmic form, and we'll need to do something else.